Hello everyone and God bless you. Welcome to this new presentation on astronomy, asteroids and comets. Introduction. Asteroids are rocky bodies that form a debris orbiting the Sun. They are much smaller than planets and they have unique non-uniform shapes and composition. There is a theory proposed by archaeologist and researcher Timothy Albedo, stating that asteroids are actually broken pieces of regular planets, which makes sense since you have different types of asteroids such as the carbon type, the metallic type, the rocky type, as if they are parts of different areas of one planet. Okay, they are broken chunks from different locations or different depths of a planet that disintegrated. They are located between Mars and Jupiter into what is known as the asteroid belt, and they travel near Earth and beyond Neptune. Others are near-Earth asteroids or NEAs, which have the potential to impact the Earth. Some are called Trojans because they follow the same orbits as other planets. Usually, they are composed of rocks and hard heavy metals such as iron and nickel, with some of them having ice formations due to their far distance from the Sun. They can actually form ice. Their sizes range from very tiny up to 1,000-kilometer wide like Ceres. Given their small size, they have a weak gravity. So let's talk about asteroids in detail. Definition and general characteristics. Asteroids are small, rocky or metallic bodies that orbit the Sun, primarily located in the region between Mars and Jupiter, known as the asteroid belt. They are remnants of the early solar system that never accreted into a full-size planet, due to gravitational perturbations, primarily from Jupiter. Actually, I believe that they are broken parts of ancient planets. Diameter range is from 1 meter to 1,000 kilometers. Low gravity environments. Irregular non-spherical shapes, since that they are broken parts of an ancient planet or ancient planets, except for largest bodies, that they can form into a spherical shape, and no intrinsic light emission. So they are visible via reflected sunlight or via the fact that they would block the background. So when you have a dark background behind them, this is how they can be detected for some types that have a lower albedo. Classification of asteroids. Asteroids are classified based on their spectral properties and composition. When we talk about spectrum, we're talking about the types of frequencies that are reflected, light frequencies or electromagnetic waves that are being reflected from the asteroid as it is being exposed or it gets exposed to the Sun. So what are the different types of light waves, electromagnetic radiations that are coming back from the asteroid, which is, by the way, a function of the albedo. Albedo is how much of the light is being reflected by the surface of the asteroid skin, and it would depend on the type or the composition, chemical structure or geological structure of the asteroid. So is it made of metals, of carbonaceous material, or organic or volcanic, etc. Some types of asteroids, especially the M type, which is the metallic type, they would reflect especially the types of waves that are radio waves. This is how we identify this is a metallic asteroid, because it's working or behaving just like a radio wave antenna. For other types, they would absorb most of the light. For some types, each light wave of the spectrum would be absorbed, so it would be almost impossible to detect them except for the fact that they are blocking the lights of different stars and galaxies behind them. So this is how you can identify them, through their motion, the motion of blocking the light that is being blocked behind them as they move. Starting with the C type, which is the carbonaceous type. So this one is rich in carbon compounds. You have dark surfaces like matte color, on the outside, they have a low albedo. Why? Because due to the fact that most of the light waves are being absorbed by the surface due to its composition. Again, as a reminder, the albedo is how much light is being reflected from the surface. And these represent around 75% of known asteroids. Another side note, this would be the asteroids that would have been broken from the surface of a planet. As for the S-type or silicaceous type, these are composed of silicate minerals and metals, so it is mostly composed of rock materials. They have a moderate albedo, so some of the light is being reflected due to the fact that they are composed of rocks and silicate, and these are common in inner asteroid belt. So that would be the middle area of the planet that has been broken, okay? Like beneath the crest, okay? The external crest, the external layer, that would be right below it. Third, the N-type, which stands for metallic. These are dominated by iron and nickel composition, which are very heavy materials. They are heavy metals, so thus this type has a higher density. Moreover, since it is made out of metals, they would represent a high albedo, a high reflection against the light, for the light. And one of the characteristic waves that would be coming back via reflection would be the radio waves, okay? Because they are behaving just like antennas, and they are likely remnants of differentiated bodies. Moreover, we have three other types that are less common and existing in much lower numbers within the solar systems, and these types are the following. You have the V-type, which you can say it stands for volcanic type, mainly made out of basalt, a very hard type of rocks. You have the R-type, so you can say that it's like the reddish type. It's made of pyroxene, so that would be a corroded iron. This is what gives it the reddish color. And finally, you have the D-type, which is made mainly of organic materials. Size distribution and mass. The size distribution of asteroids follows a power law relationship, which is n of d is proportional to d to the power of minus q, where q is approximately 2.5 for many populations of asteroids. N of d is equal to the number of asteroids with diameter greater than d. Mass of an asteroid can be approximated by m is equal to 4/3 pi r to the power of 3 rho, which is the formula. Rho is equal to m divided by the volume. Rho is the density of the asteroid, is given by the mass of the asteroid divided by its approximated volume. So, since we are considering it as a sphere, m is equal to rho times v, v being the volume, which is 4/3 pi times r, the average radius for the asteroid, to the power of 3, multiplied by the density in kilograms per meter cubed. Typical densities: the C-type or carbonaceous type, around 1.2 to 2.2 gram per centimeter cube. S-type, which is the silicate type, approximately 2.0 to 3.2 gram per centimeter cubed. And the N-type, of course, would be the heaviest and the one having the highest density, so which is around 3.0 to 5.5 grams per centimeter cubed. By the way, 3 is around the same density of the iron. Yes, iron and nickel, around that. Orbital dynamics. According to Kepler's third law, because the asteroids follow that same law and order of motion within the sky around a planet. So, for Kepler's third law, t square, which is the orbital period, okay, how long does it take for the asteroid to circle around, not circle necessarily, because they usually have an elliptical orbit, okay, but how long does it take to circle around a planet? So it is t squared is equal to 4 pi squared divided by gm. G is the gravitational constant, m is the mass of the sun, times a3, which is the semi-major axis. Okay, so semi-major axis, let's say this is the orbit. That would be the semi-major axis, A, of the ellipse. It is the distance from the center of the trajectory all the way to the first edge, okay? Semi-major axis, meaning half of it, okay? From the center to one of the edges, the longest one. Not this one. This is the minor axis, okay? So B would be the semi-minor axis. Here A is the semi-major axis from here to here. Orbital velocity. Orbital velocity is given by V is equal to square root of gm, mass of the sun around which the asteroid is circling, okay, or mass of whatever, but here we're considering the sun, divided by r, which is the radius of rotation in case it was circular. Specific orbital energy is given by E is equal to minus gm of the sun divided by 2a. Again, A is the semi-major axis. Now, in case you are asking where did we get or how did we get the velocity, okay? So here's the thing. If you are moving about a circular orbit around the sun, you would have a gravitational force equal to the centrifugal force, which is the force generated by the rotation motion around the sun, okay? So gravitational force is given by G, small m, which is the mass of the asteroid, times m of the sun, divided by r square, which is the distance to the center or radius of rotation, okay, is equal to lowercase m v squared over r, correct? So here we can factor out the radius. We remain with 1r and also m. So you get v is equal to the square root of gm over r. Gm of the sun, which is the O dot symbol, divided by r, the radius of rotation. Asteroid families and groups. Main belt asteroids located between 2.1 astronomical unit AU and 3.3 AU from the sun. By the way, AU or astronomical unit is a relative unit, which is the distance between the sun and the earth. So we took it as a reference measurement unit to measure very long distances, which are astronomical distances. Near-Earth asteroids and NEAs. Okay, objects whose orbits bring them close to Earth. Subcategories include Atira group, Aten group, Apollo group, and Amor group. Trojan asteroids, asteroids that share the orbit of a planet at Lagrange points, L4 and L5. Surface properties and albedo. Okay, so albedo is defined again as the fraction of sunlight being reflected from the surface of the asteroids. It is given by A equal reflected radiation divided by incident radiation. So it is a ratio between the reflected radiation versus the incident radiation. The light that is being returned from the asteroid's surface, external surface of course, divided over the light that is incident, to which the asteroid is being exposed. Brightness relation, F, which is the observed flux, is given by A, or albedo, times the luminosity of the sun, which is a reference luminosity value, divided by 4 pi d squared, which d is the distance from the observer. And of course 4 pi, 4 times pi. So this is how we can get the distance, by the way, by measuring the returned flux. Rotation and shapes. Asteroids exhibit rotational motion. So omega, or angular velocity, is given by 2 pi divided by t, where t is the rotation period or the time it takes the asteroid to circle around the sun. To complete one full cycle. Light curve variations allow determination of rotation period, so how long does it take the asteroid to go around for one cycle. Shape irregularities. So what does the shape of the asteroid look like? We can observe, or like we can map the surface. And finally, the binary systems. Binary systems here mean when you have two fragments of the asteroids that are rotating together, being affected by their mutual gravity to stay along, as two bodies forming one collective, one group, but it is made of two bodies attracting each other and flying along each other. Internal structure. Asteroids may be monolithic, solid rock, and robopiles, which means gravitational aggregates. Or you have multiple composites, multiple different chemical compositions within the same body that have, attracted each other, and they are stuck with each other within one body, but they are not uniform. It's not a homogeneous structure, so to speak. The escape velocity from the surface is given by VE is equal to square root of 2gm over r. M being the mass of the asteroid, g of course is the gravitational constant, and r is the radius. Low escape velocities explain lack of atmospheres. In other words, when you don't have a thick atmosphere around the asteroid, the velocity would be enough for the body to escape from the attraction, from the gravitational field of the asteroid, because it won't be damped down and slowed down enough for the gravity of the asteroid to pull it downward, to suck it down. Collisions and evolution. Collision frequency is significant in the asteroid belt. Kinetic energy of collision is given by E is equal to 1/2 mv squared. The effects are fragmentation, crater formation, and creation of asteroid families. Now, the most significant aspect of the kinetic energy is in the study of impacts that we will get to later. Thermal-Yarkovsky Effect. This is defined by a small force that would be generated due to the fact that the asteroid surface is being exposed to the sunlight or solar energy. So it is a small force induced due to anisotropic thermal emission. If the force is proportional to P over C, where P is the radiated power, radiated thermal power, so to speak, divided by C, or the speed of light. This effect causes gradual orbit drifting over long time scales or long distances. To give a simple analogy, okay? So let's say you have someone who plays basketball. You notice something, that when he would throw the ball out of his hand, he would have a pushback, which means that this same motion would cause a recoil. His body would be pushed backwards. This goes along also the third law of Newton of action and reaction. So for every action, there's an opposite and equal reaction. When you throw something out of your hand, your body also would be jerked backwards with the same force versus mass. The formula goes this way. M1 V1 is equal to M2 V2. Mass 1 times velocity of 1, the first object, is equal to mass 2, let's say myself, times V2, the velocity of recoil. Going back to the asteroid, this is how it works. So the sun, when it hits the surface of the asteroid, it would start heating up the surface, which causes evaporation of different types of material that become aerosol, okay? They would start being pushed into the atmosphere of the asteroid, creating something like a jet stream. This jet stream would create a force that, after a very long period of time, this force, depending on its direction of course, would start drifting the asteroid away from its original trajectory. Interestingly enough, there's a description of an asteroid impact in the book of Revelations, chapter 8 in the Bible, where it portrays a massive rock falling from the sky, actually another translation, a massive mountain falling from the sky, and it's named wormwood, which is another word for bitterness. The original word in Greek is aphesentin, or bitter, another translation. So, then the second angel blew his trumpet, and a great mountain of fire, that would be an asteroid, from the eye of the beholder, okay, he couldn't describe it other than a mountain of fire, which was John the Revelator. So a great mountain of fire was thrown into the sea. 1/3 of the water in the sea became blood. And here's why it became blood. 1/3 of all things living in the sea died, and 1/3 of all the ships on the sea were destroyed. So this was an amazing prophecy, because no way you would have imagined that there would be, this amount or this large number of ships traveling today in different international seas. Then the third angel blew his trumpet, and a great star fell from the sky, burning like a torch. It fell on 1/3 of the rivers and on the springs of waters. These would be meteors, by the way. These would be fragments going before the main asteroid. My assumption. The name of the star was bitterness, or wormwood, or aphesentin. It made 1/3 of the water bitter, and many people died from drinking the bitter water. Then the fourth angel blew his trumpet, and 1/3 of the sun was struck, and 1/3 of the moon, and 1/3 of the stars. And they became dark, and 1/3 of the day was dark, and also 1/3 of the night. Now this one is kind of cryptic. Okay, we'll try to break it down. This is Revelations chapter 8, verses 9 to 12. Now, personally, I believe that this is due to the rubble being thrown in the air after the impact of the asteroid. It would block partially both the sun, the moons, and the stars also would be darkened. Why? Because no more light can be going through the atmosphere due to the rubble and dust and smoke that has been thrown in the air due to the impact of the asteroid. Now again, concerning the 1/3 being blocked, 1/3 of the light of the sun, of the stars, actually it literally says 1/3 of the sun was struck, 1/3 of the moon, and 1/3 of the stars. I completely believe that he's speaking about the light spectrum. This is the 1/3 he's referring to. 1/3 of the light spectrum being blocked by the dust and smoke that was thrown in the air. So you have the different frequencies of light from infrared to ultraviolet. Of course, we're more concerned here about the visible spectrum, which is red to violet, correct? So 1/3 of that was blocked due to the fact that for higher frequency waves, they can no longer penetrate through a thick layer of smoke. That's why. Only the red waves can survive that. Why? Because they are longer waves. From a physics perspective, how can light be partially blocked? You see, in the theory of telecommunications, for a wavelength, an electromagnetic wave to go through an obstacle, lambda, which is the wavelength or the distance between two consecutive peaks or two oscillations, should be greater than or equal to the thickness of the obstacle. This is how it works. So longer wavelengths are actually in the range of the red light, okay, red wavelengths. But for violet and blues, these are high frequencies which would be blocked by, the atmospheric contamination of smoke and dust due to the ejection of the soil and the smoke of burning after the asteroid hits the Earth. In Matthew 19:29, immediately after the tribulation of those days, the sun will be darkened due to the blocking of dust and smoke, and the moon will not provide its light, and the stars will fall from the sky. These would be probably planetary fragments and asteroids, and the powers of the heavens will be shaken. Another sobering hint for that is in Joel chapter 2:31, that's in the Old Testament. The sun will be turned into darkness, and the moon into blood before the great and terrible day of the Lord comes. Now it's interesting. So why is the sun almost fully blocked? But it doesn't necessarily mean that all the wavelengths cannot go through, except the fact that these wavelengths remaining are not perceptible or visible by the eye. However, for the moon, it will turn into blood. Now, this doesn't mean that it will literally turn into a bloody surface, but what remains of the light spectrum that can still go through the clouds or like the darkened, smoked and dust within the air, that would be the longer wavelengths and literally the red light. So only the red can go through. This is why the moon would seem as a blood moon, so to speak. This is commonly known as the blood moon. So this is due to the fact of a partial blockage of the wavelengths of the sun, and only longer wavelengths such as the red one would be able to get through. This can also, of course, be alluding to a solar eclipse. And more than that, now, if we consider that the sunlight had completely been blocked, this would be due to the fact that the sun is located at a very far distance, so the light wouldn't be able to get through. Meanwhile, the moon that is reflecting the light, since it is at a proximity from the atmosphere of the Earth, it would still go through via the red wavelengths. Now, the kinetic energy generated from an asteroid impact is 1/2 of the product between the mass of the asteroid times the square of its velocity. Kinetic energy usually is measured in joules, mass in kilograms, and velocity in meters per second. So the energy generated by the asteroid that caused a mass extinction called Chicxulub, which impacted in the Yucatan Peninsula in Mexico, was around 10 to 15 kilometers wide, which is 6 to 9 miles. Estimated mass 1 or 2 times 10 to the power of 15 kilograms, or 1 to 2 quadrillion kilograms, and a velocity of 20 kilometers per second, or 45,000 miles per hour. The energy released was 100 million megatons, or TNT. The impact created a crater of around 180 kilometers, 110 miles wide, and 20 to 30 kilometers, 12 to 18 miles deep. So we're gonna exploit how to estimate the crater's dimension, whether the diameter and the depth, based on the velocity of the asteroid and its estimated mass. Due to the irregularity of the shape of asteroids, there is no fixed formula that can give us the crater widths and depths generated based on the width, weight, and the speed of impact of an asteroid, since there are other factors such as the soil structure and asteroids' chemical makeup involved, which would give us the stiffness of the asteroid after impact, whether it will disintegrate immediately or it will hold up to a certain depth. However, looking into data collected from past impacts throughout the world history, we can have an estimated formula. Starting from Poppygay crater in Siberia, the asteroid width was around 5 to 8 kilometers, traveling speed around 15 to 20 kilometers per second. The weight, 10 to the power of 13 or 10 to the power of 14 kilograms. So the crater width generated was 100 kilometers and the depth 20 kilometers. Tunguska event, Siberia, asteroid width 50 to 60 kilometers, traveling speed 15 to 30 kilometers per second, weight 10 to the power of 7 kilograms. Crater width, no crater, but the shock wave flattened around 2,150 kilometers square of forest. So there was no crater. It almost blew up and completely exploded on the surface. Verderford crater, Siberia, asteroid width around 10 to 15 kilometers, traveling speed 15 to 20 kilometers per second, weight unknown, crater width around 250 to 300 kilometers, and the depth around 20 to 25 kilometers. This data collection stemming from different events is necessary so as to estimate or to discover the relationship that correlates between the weight of the asteroid, traveling speed, and the width. Width meaning, the longest distance between two edges of the asteroid. So how to correlate them with the crater width, the width of the crater generated after impact, and its depth. So we find out that the crater width is approximately equal to the product of the width in kilometers, the width of the asteroid, which is the longest distance between two edges, multiplied by the impact speed, also in kilometers per second. The crater depth, that would be 10 to 20% of the crater width. For instance, Poppygate crater in Siberia. The asteroid width was around 5 to 8 kilometers. The traveling speed 15 to 20 kilometers per second, correct? The weight around 10 to the power 13 or 10 to the power of 14 kilograms. So the crater width is around 100 kilometers, which is 5 multiplied by 20. Of course, this is an approximation. The crater depth is around 20% of the crater width, which is 20 kilometers. This is due to the fact that the weight is above 10 to the power 13 kilograms. So the crater width is given by the asteroid width multiplied by the impact velocity or distance, the longest distance between two edges of the asteroid, multiplied by its impact velocity. In our case here, you have Poppygate crater, 5 to 8 kilometers width, traveling speed 15 to 20 kilometers per second at impact. So it is around, let's say we choose 5 multiplied by 20, that would be 100 kilometers. As for the crater depth, it is given by this formula. It is equal to the power, which is the power of the mass. So you have here 10 to the power 14. You take 14 divided by 7, that would be 2, multiplied by 10 divided by 100, so 20%, multiplied by the crater width. So 20% of the crater width, which is 20 kilometers, 20% of 100. In case the weight was less than a value n multiplied by 10 to the power of 7 kilograms, so it would be 7 divided by 7, times 10 over 100, that would be 10% of the crater width. So the crater depth would be equal to 0.1 times crater width. Tunguska event, Siberia. So the asteroid width was there 50 to 60 kilometers, traveling speed 15 to 30 kilometers per second, weight around 10 to the power of 7 kilograms. Crater width, no crater but shockwave that had flattened around 2,150 kilometers squared of forests. So how to measure the range of the blast in such case, since we have no crater? The shockwave or blast area is estimated in such case by multiplying the asteroid width with the impact speed added to 10% of the answer. In other words, the 10% that we used to measure up for the depth of the crater, that would be added to, like the 10% times that value, okay? That would be added to velocity times the width of the asteroid. So the blast area is given by asteroid width in kilometers times impact velocity kilometers per second plus 0.1 of the same product. Here in practice, let's apply this rule for Tunguska event itself. So you have asteroid width, we're gonna take the upper values here. Okay, so asteroid width, which is 60 kilometers. Speed, we're gonna take 30 kilometers per second. So, crater width, or actually not crater width. So let's evaluate the blast area. Blast area is equal to asteroid width times speed, 60 times 30, which is 1,800, plus, since we have 10 to the power of 7 kilograms, so the power is 7. Remember, we divide by 7 the power, so it is 1 here. You take 10% of the entire product. This was usually designated for the depth, but here, the measurement that was dedicated for the depth, you added to the crater width to get the blast area. So plus 10% of the 1800, which is 180. So it is 1800 times 180, approximately 1980, which is very close to 2150 kilometers. For Poppygate crater, asteroid width 5 to 8 kilometers, traveling speed 15 to 20 kilometers, weight approximately 10 to the power of 13 or power of 14. So, crater width is equal to asteroid width times impact velocity. This is 5 kilometers. We're taking this low value times 20 kilometers, the high value, equal around 100 kilometers in order to fit for the data that we have. Okay, it is an estimation anyway. Crater depth is equal to the power of the weight, which is 14. We're gonna take the higher power, divided by 7. It is 2 times 10%. Okay, so it becomes 20%. To put it simply, multiplied by the crater width, it gives us 20% of the 100, which is 20 kilometers. Asteroids, metallicity detection and measurement. In an attempt to identify the metallicity and chemical structure of an asteroid, scientists use a method called spectroscopy to determine its composition. Now, what do we mean by that? First, collecting reflected light via telescopes, which is a large spectrum of frequencies ranging from near-infrared to visible light, measuring the spectrum and identifying the wavelengths and their respective magnitudes within the signal. So this is how we get the albedo, or in other words, how much light has been reflected, how many wavelengths and their respective power that have been reflected from the asteroid. This is how you can identify the chemical structure. Hence, any bands that were absorbed are identified by looking at a plunge in intensity of certain wavelengths, a dip in intensity. Now, based on lab experiments, different metals absorb and reflect different wavelengths, which can give us a fingerprint of the type of metal we're dealing with within the asteroid. Another important thing to notice here is that we can get the mass of the asteroid based on different parameters. The first one would be the velocity of rotation around the sun, given by V is equal to the square root of gm over r, where m is the mass of the sun in this context and r is the radius of rotation. Once you get the velocity of rotation, you can place it in the formula of the centrifugal force, which is given by F centrifugal equal to m, lowercase m here, times v square over r. We already have the radius of rotation and the velocity, which is the tangential velocity. So we need to evaluate m, and we get m, lowercase m, that would be the mass of the asteroid, based or from the centrifugal force, which is in circular orbits equal to the gravitational force Fg, given by g, lowercase m, mass of the asteroid, times mass of the sun, O dot, divided by r square. So here, this is the mass of the sun represented by m, O dot. Again, what characterizes metallic structures is their high reflectivity and, as a consequence, a shallow light absorption. So they have a flat and featureless spectrum in the visible and near and infrared. In other words, the reflected light has the same amplitude for different frequencies. So there is no ups and downs within the reflected spectrum due to a high albedo, or in other words, a low absorption level of different frequencies, because a metallic surface is highly reflective. Featureless here is almost the same word, which is implying that there is no feature of ups and downs or no unique fingerprint of different frequencies being absorbed when we are dealing with metals. Most frequencies, if not all of them, would be completely reflected. Another feature is that they have a strong reflectivity toward radio signals. This is what explains why antennas are made out of metals, especially iron, because they have the ability to reflect radio waves, especially for dish antennas. So let's observe this table here. So for a wavelength around 0.4 to 1 micrometer, the feature would be flat or slightly red slope. Interpretation, this would indicate metal or silicat. Wavelength around 0.9 micrometer, feature weak band. The interpretation would be oxidized metal or pyroxene, okay, like a corroded iron. Wavelengths greater than 2.0 micrometers, no strong water features. That would be a dry or possibly metallic aspect of the metal, okay, of the surface, and radar being returned or radar signal being returned. So the feature is strong and high metallic content is being revealed by this spectroscopy. As we notice in the upper table, longer wavelengths such as radar radio waves are the most reflected by metallic surfaces, unlike shorter wavelengths which would be absorbed. What would be the reason? This is due to metals having an abundance of free-moving electrons that respond to the oscillating electrical field of an electromagnetic wave or frequency. At longer wavelengths, such as the radars, the metal's electrons have enough time to oscillate in phase with the EM waves. This in-phase movement leads to a strong reflection rather than absorption, so the metal surface acts like a mirror, just like a satellite dish, to a radio transmission from a satellite. Meanwhile, for shorter wavelengths or higher frequencies, the electrical field bounces too fast for the free-moving electrons that are on the surface of the metal to resonate with it. So, it gets either absorbed by the metal or scattered by the surface instead of being reflected. Now let's take a look at different spectral fingerprints for different types of metals, noting that it's not always an accurate approach given that asteroids can have irregular residues on their surfaces coming from different types of metals. Starting with iron or Fe, so it has a flat or slightly red sloped continuum, shallow band around 0.9 to 1.2 micrometers. Reflectance characteristics, flat spectrum in the VNIR, which stands for the visible near infrared. Notes, pure iron is highly reflective at radar wavelengths, which are longer wavelengths. Nickel and I, similar to iron, little to no distinct absorption bands. Reflectance similar to iron or Fe, often alloyed with iron, so you have Fe and nickel alloyed together, melted or molten together, typical of M-type asteroids. Iron oxide, FeOA or Fe2O3. You have a broad band around 0.9 micrometer or 0.6 micrometer, so absorptive, reddish spectrum, seen in weathered or oxidized iron surfaces. The iron surfaces that had corroded due to weather, due to water. Magnesium, Mg, lacks strong bands in VNIR, low to moderate reflectance, usually detected as part of silicat, e.g. olivine, pyroxene, rather than pure magnesium. Okay, so lacks a strong band in the visible near infrared. Okay, so it has a low to moderate reflectance. In other words, it has a lower albedo because the returned light is much dimmer. So higher absorption basically. Aluminum, Al, very high reflectance in ultraviolet and visible. Reflectance characteristics, very reflective but featureless. Okay, spectrally flat, this is why it's featureless in the VNIR, better detected in ultraviolet spectroscopy. Titanium, Ti, weak absorptions around 0.5 to 0.6 micrometers in oxides, low albedo overall. In other words, the absorption is very high for the different light waves of the spectrum. Copper, Cu, strong reflectance in red, so it mainly reflects the red wavelengths, absorption near around 0.58 nanometer, reddish spectrum, and rare in asteroids. So you would see it in reddish color. Chromium, Cr, possible weak band around 0.43 micrometers. It has a low albedo, in other words, very high absorption. often detected in chromite used as an indicator mineral. On a final note, in case it wasn't clearly stated, VNIR stands for visible near infrared. In other words, all the frequencies of the spectrum that are visible to the eye, but that are close, within the visible range, okay? Close to the infrared. Featureless means that there are no obvious dips or spikes in the bands. So different frequencies are reflected with the same power almost within the spectrum. The spectrum is fully reflected. It has the same level for different frequencies. Featured, however, means that some bands in the spectrum have been absorbed, so it would display something like that. Some frequencies would be absorbed, so they would have a lower reflectance and a lower power of detection. Meanwhile, for other frequencies, they would be highly reflected with low absorption. For the ones with higher absorption, they would have a lower reflectance or low albedo. Personally, I do believe that asteroids are fragments of planets, as Timothy Alberino stated, unlike the mainstream theory stating that these were formed since the inception of the universe by matter. It can be so, okay, for some cases, by matter gravitating to each other and forming some planets and others asteroids. No, for me personally, I believe that these are broken parts of planets. So the part that detached from the planet will determine whether it is C, S, or M type. So if the fragment broke off the crust of the planet, it will be mainly of water and carbon, forming the C-type asteroid. If it broke from the mantle, which is the layer between the crust and the core, okay, it is the inner area underneath the crust and apart from the core. It will be in part silicate and in another part iron or another type of metal, which will produce the S-type asteroid. Otherwise, if it detached from the core, it will be mostly metallic, which gives us the shiny M-type asteroids that are heavier and glossier. As for meteors, meteors are small rocks or particles traveling in space. Once a meteor penetrates Earth's atmosphere, it will burn due to its friction with Earth's atomic particles, producing a trailing flash of light. Same thing for asteroids, by the way. However, the meteors won't survive the burn. They would be completely consumed by the atmospheric layers. Due to its small size, most of it burns and evaporates without reaching the ground once it is absorbed by the Earth's gravitational pull, and whatever piece survives, it will land on the Earth's surface. As for other planets or moons, such as the Earth's moon, an impact from a meteorite will form a hole on the Earth due to the absence of a shielding atmosphere unlike the Earth, which explains why other planets and moons have a porous surface. They got hit so heavily by different meteors, such as the surface of the moon also. Let's talk about comets. A comet is a celestial object made primarily of icy gases and liquids like water, CO2, ammonia, and methane. When it travels close to the sun, these icy gases start evaporating immediately in a sublimation process, which is the sudden transfer from a solid state to a gas state without passing into a liquidation phase. And they form glowing trails, trailing millions of miles behind the comet's center of gravity. This glowing tail is called a coma, and usually it produces at least two tails, of which one points away from the sun due to the solar wind, and the other in a different direction due to the radiation pressure phenomena, which is the force created through heat. Most comets originate from the Kuiper belt, which is beyond Neptune, or the distant Oort cloud. They travel in highly elliptical orbits, some taking thousands of years to completely orbit the sun. The nucleus, which is the main comet mass, is usually between few to tens of kilometers across. As for the tail, it can stretch millions of kilometers behind the comet. So what is the anatomy or the structure of the comet? Let's start with the nucleus. It is the solid frozen part that harbor multiple iced gases and layers, iced water, and some dust. Coma a cloud of gas and dust forming the atmosphere surrounding the nucleus that is created by evaporation when the comet is nearing the sun or it is being hit by the sun's radiation. The ion tail. It is a stream of ionized gas pointing away from the sun due to the solar wind. More info in the next slide, of course. As for the dust tail, which is the stream of dust particles trailing behind the comet in the opposite direction of the path, of the motion, but within the same curve of trajectory. But, however, in the opposite direction of motion. This is due to the fact that it's being hit by radiated power, which gives it momentum so as to push it away from the asteroid. Starting with the ion tail, how it forms. When the comet comes near the sun, the icy components evaporate due to the heat without passing in the liquid state, in the process that is called sublimation in physics, which is a direct transfer from a solid state into a gas state. The UV solar radiation, which has a very high frequency and thus a higher energy, strikes the gas molecules such as NO2, H2O, and CO2, releasing electrons in the atmosphere. The electrons, as they get charged and excited by ultraviolet photons, pick up higher trajectories in the atom, above the atom nucleus, until they can no longer be held by the gravity of the nucleus itself. So this is when they detach from the atom, becoming ions, becoming like free electrons. And the gas become an ion. Why? Because it has become charged. As a result, these gas molecules that were neutral lose their electrical equilibrium after losing electrons and become positively charged. This leads to positive ions and liberated electrons flying above the comet. So H2O plus UV photon would produce H2O plus, positively charged H2O molecule with a free electron. When the solar wind, which is a stream of charged particles, come, it sweeps the floating ions and electrons that were released prior by the IMF, Interplanetary Magnetic Field. It carries with it, picking up these particles and transporting them away from the sun by the electromagnetic forces within the solar wind. This eventually creates the ion tail facing away from the sun. The dust tail. Just like in the case of the ion tail, the sun sublimates the icy gases of the comet that detach from the surface and float above the comet nucleus. The radiation pressure, which is by definition the force exerted by the sun photons, that although are very tiny and light, they still carry a certain momentum, pushing the floating particles away by exerting a tiny force, a tiny push. The dust grains get lightly and gradually pushed by these photons, and they trail behind the comet's orbit. Of course, the lighter these dust particles are, the farther they are pushed away in or within the comet tail, and vice versa. Finally, unlike the ion tail, which has the form of a line, the dust tail is more curved due to the disparity of the masses that are being projected. Masses of the dust particles and different aerosol material, so to speak, and the gravity exerted against them by the nucleus, since they are heavier than gases. And you have different masses for different types of particles that are being pushed away by the radiation power of the sun, which is the photonic electromagnetic force. So the comet consists of different or distinct components such as H2O, carbon dioxide, and carbon monoxide mixed with dust and rocky material, which makes sense, by the way, concerning the icy structure, since they are moving most of the time away from the sun and they come from, different extra or external sources outside of the planetary system. So they would be icy most of the time. Now, the solid core, again composed of ice, H2O, CO2, and CO. The mass approximation is given by 4 divided by 3 pi r3, which is the radius, the average radius. In case we want to average the shape, the irregular shape of the comet core to a sphere, that would be the radius of that sphere. 4/3 pi r3, that would be the approximated volume, multiplied by the rho, which is the average density. M equal rho times V, that would be the estimated mass of the comet. Comma, a diffuse gaseous envelope formed by sublimation of ices. The gas expansion velocity is given by V gas approximately equal to square root of 2kT divided by M, where K is the Boltzmann constant, T is the temperature, I think in Kelvin, and M is the molecular mass of the gas being expelled. As for the ion tail, it's composed of ionized gas that has become electrically charged due to the fact that it had lost electrons. Electrons have been freed. Also, this is caused by the sun radiation that had excited these electrons. They kept going up within the energy band of the atom until they were released. So they roam free as free electrons. Meanwhile, the gases themselves became positively charged as a result for that. So directed away from the sun by solar wind, force due to solar wind is given by F is equal to QE plus QV times B. V is the velocity of the gas, B is the magnetic field, and E is the electrical field, while Q is actually the charge of the particle, okay? The charge of the proton, I think. Dust tail, composed of small solid particles, curved due to combined gravitational and radiation pressure forces. The radiation pressure force is given by F radiation equal to the luminosity of the sun times A, which is, I think, the albedo, the reflected light coming from the comet in this case, divided by 4 pi r square C. 4 pi r square is the surface, the equivalent surface of the sphere. If you can consider the comet core as a sphere, that would be 4 pi r square times C, which is the speed of light. Comet brightness. The brightness of a comet depends on its distance from the sun and Earth. So it is inversely proportional to the square of the radius. I'm sorry, that would be, the radius of rotation, which is the distance from the sun, and delta square, which is the distance from the Earth. Now, empirical magnitude formula is given by M equal H plus 5 log delta plus 2.5 n log R. H is the absolute magnitude, and n is the activity parameter, okay? Absolute magnitude of the brightness, and n being the activity parameter. Thank you so much for watching, and see you next time.